thank you for coming. Tonight, we have another exciting and a key public lecture by Oxford professor Subir Sarkar, testing the cosmological principle. Please welcome the speaker.
Well, when Professor Alikram asked me to give a public lecture, I was a little disconcerted because earlier it was going to have been a topical seminar, but fortunately I had kept it at the level of a colloquium, so I think hopefully that will suffice for the purpose intended. And there is some overlap with one of the lectures I gave, because this is the topic you wanted to hear about, and it is indeed of wide interest, so why not focus on this particular question, and I'll explain why it is important. So what this shows is a large-scale simulation of the universe. This is from Dark Sky, one of the largest simulations ever done, and it shows us by the by now familiar so-called cosmic web of galaxies, which is actually colored in density enhancements in a sea of dark matter. We don't actually know exactly where the galaxies form, but you get the picture that this is something that you expect from gravitational instability, and statistically it is homogeneous. There are obviously large sheets and filaments and all that, but we start from small perturbations in a homogeneous universe, and the net result is, although it has lots of interesting structure, is statistically homogeneous. Now, the philosophy I'm going to adopt in this talk is that which I learned from Dennis Sharma, who I had the privilege of working with briefly in Oxford when I first went there. And he said in an interview that none of us can understand why there is a universe at all, why anything should exist. That's the real question. But while we can't answer this question, we can make progress with the next simpler one of what the universe as a whole is like. Now, the reason I emphasize this is what I learned from Dennis is that theories should look at data. We should not simply accept, ideal principles such as the one that this simulation is based on, namely the idea that the universe is exactly homogeneous and isotropic. So I want to take you through what we have been looking at for the last few years, asking experimentally, is that really true? So this slide I showed earlier to emphasize in my talk that there are limits to what we can know in cosmology, because everything that we know is contained within our light cone, and we cannot move somewhere else and construct another light cone and check that the universe looks the same from over there as from here. So we are necessarily, there is something called cosmic variance, which is the fact that the observer can be anywhere within this fluctuating density field that you showed in that, that was shown in that cartoon, and therefore the view that you will get will depend on where we are, and this goes by the name of cosmic variance. This does not affect structure on very small scales, which is more or less the same everywhere, but it does affect structure on large scales. Now, the model of the universe that we work with, we have discussed that in 2 lectures, and I summarized that in one slide here. So you start with these assumptions, isotropic and homogeneous, and that allows us to adopt the Robertson-Walker metric, which describes maximally symmetric space-time, and we populate that with an ideal fluid for the energy momentum tensor, which is just diagonal. And that Robertson-Walker metric I have written here in using conformal time, just so that it looks like a Minkowski metric. The idea is that we can then map the entire universe, this hypersphere that I talked about, where we are at some point and the Big Bang is the opposite point of the hypersphere. This is projected onto 2 dimensions here. So here we are at the center of the universe, that's where we belong, right? And the Big Bang is this surface of infinite redshift, which is the antipodal point of this hypersphere. and the radial coordinate is conformal time, or if you like redshift, and that is marked here. So all of astronomy, or most of astronomy, used to be done within redshift of 1, in fact very close to us, redshift of 0.1 or so. But today we actually observe galaxies out to redshifts of order 10, and we observe the last scattering surface of the microwave background at 1000, in between of the so-called dark ages, which we hope to soon probe using 21 centimeter topography. Beyond that point, the universe is opaque, so a photon which starts out at the Big Bang will be random walking in the plasma, and by the time, while it is doing so, the universe is expanding and getting more dilute, and by the time it hits 1000, as you saw in the lecture, we can calculate the ionization fraction drops like a stone, universe certainly becomes neutral, the last scattering surface is well defined, and therefore we actually see anisotropies imprinted on it which have been laid down at earlier times, and we can see by constructing the past light cones of 2 points on this last scattering surface that they are causally connected only if they are within about 1 degree. This angle is 1 degree times square root of omega. So it's also a measure of the curvature of space-like sections, and outside that, points are not causally connected, but we observe them to have the same temperature to within 1 part in 10 to the 4 or so. And this means that whatever laid down those fluctuations operated on super horizon scales in the standard cosmology. Therefore, something must have happened to the standard cosmology at early times, and you know there are one easy way to erase that is to have a period of exponential inflation. But you should also be concerned, because I also pointed out to you in the last lecture that in order to make that argument, one has to construct the light cone back to T of 0, and we really don't know how to do that in a sensible way, because there may be no metric at T of 0. So the usual argument for the horizon problem is actually suspect. It's a convenient argument, it works in the FRW cosmology, but actually FRW cosmology certainly does not hold back to the Planck time, and unless you can do that, you cannot really argue for the horizon problem. Be that as it may, today we are sticking to the standard picture, but all I'm trying to emphasize is that every one of these apparently innocuous arguments actually invites questioning, okay, whether that really is a tight argument. So as I also told in the lecture, when you populate the universe with an ideal fluid for this T mu nu, and you reduce Einstein's equations to just 1 using the Robertson-Walker metric and the ideal fluid, you get Friedmann's equation, which has just 3 terms. The scale factor changes governed by the energy density in matter, that includes radiation, the curvature of space-like sections, kappa, that's the sign, and a cosmological constant, which you can add to this equation taking advantage of the general coordinate invariance that this exhibits. So you have therefore written out this thing you can write suggestively as a matter component that obviously redshifts with the cube of the redshift. If it was radiation, it would go as the 4th power, but some high power. And then the curvature goes as a square, so it's unimportant in the early universe, as we saw this morning, and this is very much unimportant in the early universe. But and these are the 3 components defined there, and that gives you this cosmic sum rule, which we briefly discussed in a question after my first lecture. And therefore, essentially this picture is summarized in this sum rule, and then you try and measure these things, and in fact what you find, as we discussed, is that this comes out to be close to 0 when averaged over the entire distance to the last scattering surface. Locally, curvature is not 0. I want to emphasize that. If you are in a low density region, there is negative curvature. If you are in a high density region, there is positive curvature. But the average curvature of space-like sections is 0. Okay? That does not mean that you cannot have curvature locally. Matter, we find, is insufficient to make up the critical density. This turns out to be about 0.3. So therefore, omega lambda, you get to be 0.7. And we have already mentioned that that corresponds, because lambda is defined as so. This corresponds to lambda being of order h0 square, which is the scale of the universe, the scale of the Hubble radius. So that's 10 to the 28 centimeters, or in energy units, it's 10 to the minus 42 GeV, not one that we know of in any fundamental physical theory, right? So unless one can think up some kind of infrared ultraviolet connection, it is not clear at all how this object here, which is actually the sum of this lambda on the left hand side and the super renormalizable term in the Lagrangian on the right hand side, let's say, which might be of order TeV to the 4th power in the standard model, how they conspire together to give you something of order 10 to the minus 42 GeV, anyone's guess, right? And indeed, anyone does guess. There probably have been about 5,000 papers putting forward such guesses. But let us address the basic issue. This is a quote from somewhere which outlines that surveys of type 1 supernovae have indicated an acceleration of the expansion. This requires the assumption that the universe is isotropic and homogeneous. Then this acceleration implies a fluid with negative pressure called dark energy or a cosmological constant, or it might imply modifications of gravity. And there has been a huge industry in the last 20 years, since 2000 or so, to explore these possibilities. With, I would say, at best mixed success, in the sense that these explorations have not been entirely pointless. They have delineated many aspects of gravity that are interesting. In attempts to deviate from Einsteinian gravity, you kind of realize just how tight the structure is and how difficult it is to modify gravity, as it were. And having kind of a dynamical cosmological constant in the form of a scalar field, that of course is just as fine-tuned as a cosmological constant, as we will show you. So that is, in fact, the first slide tells you that this T mu nu contains also a cosmological constant. So the real cosmological constant that affects cosmology is in fact the sum of, if you like, the bare constant which multiplies G mu nu and the contribution from the fields. And this is the object that we are finding to be of order h naught square. Now, if you interpret this as vacuum energy, in which case you have to multiply this by Planck mass square, and so the energy density then is h naught square times Planck mass square to the 1/4 power, so that's about 10 to the minus 12 GeV. Then that is of the same order as the matter density today, 10 to the minus 3 eV. Everything is of the order of 10 to the minus 3 eV. Why is that? So one possibility is that it could be some evolving ultralight scalar field with a nice name, because this can actually, if you look at the coupled equations of quintessence and so on, the energy density of matter and the scalar field converge. There is a attractor, so they will become of the same order. There is a dynamical reason. However, in order to make that happen, you have to make the curvature of this scalar field, which is of order the Hubble parameter. Otherwise, the scalar field will not evolve. It will be just stuck. So that has to be of order the Hubble parameter. But the height of the scalar field will be what I just said, the geometric mean of h naught square and Planck mass square. So that's 10 to the minus 12. So you see there is 30 orders of magnitude hierarchy there. And of course, you have to take the 4th power of it for the energy density. So it's a hierarchy of 10 to the 120. Exactly the same fine-tuning problem as the cosmological constant problem. So there is no difference. You don't learn anything from doing this, apart from how difficult it is to construct a potential for this quintessence field, which is so flat that, if I constructed it, if I did the usual Mexican hat potential, imagine this is 1 meter high, then the minimum of it will be beyond the universe. It will be more than 10 to the 30 centimeters away. That's how fine-tuned this potential is. Now, people, of course, have tried other approaches. For example, you could say that perhaps the problem all arises because gravity is so much weaker than the other forces, effectively in the sense that this infrared scale of the universe is not the Planck scale, which is very, very small. That is the only scale in gravity. It is huge compared to the Planck scale. So the hierarchy between the Hubble radius and the Planck scale is essentially what we are trying to address. Now, DGP Brain World says that gravity starts propagating in more dimensions on some scale, and that explains why gravity is so much weaker. And that also then provides a way to explain this acceleration. However, you have to put this scale in by hand, because you would expect this behavior to happen at the only scale in gravity, which is the Planck scale. But you have to actually put this in by hand at the scale of the Hubble radius. So the fine-tuning in all proposals to explain this is just as bad as the bare cosmological constant. You don't improve in any way. In fact, you usually generate a second problem. Okay? You could, for example, there are now theories of massive gravity, where the graviton has a mass which apparently are ghost-free, they are sensible. However, if ordered to make them relevant to cosmology, you have to give the graviton a mass, you guessed it, of order the Hubble parameter. So there is no way you can escape the Hubble parameter in any attempt to understand or explain what you see. Okay, and therefore, you can get even more baroque. People think of fields which apparently are screened by matter, so by construction you can't ever investigate them where you live on the planet because there is matter there. So, one tends to get suspicious of theories that are constructed so as to evade experimental tests, right? As I told you in the BBN lecture, you would get around the why now problem if lambda was always of order h square. And there are serious quantum gravity people I know who try to, recover this. But this is actually totally easy to dismiss, because if lambda was always of order h squared, then why can't I just take it on the left-hand side, and that would imply just a rescaling of Newton's constant. Right? So it would not give me accelerated expansion, and it would also it is also ruled out phenomenologically, because we saw that nucleosynthesis actually bounds Gn to be within a few % of its lab value, right? So that's a non-starter. So I claim that there is no physical explanation for the coincidence problem. There cannot be, right? Now, therefore, one is inclined to wonder if lambda might be of order h0 square, as is required to explain the observations allegedly, because that's just the observational sensitivity we have, right? There's some arbitrary parameter lambda. We fit that, determine that by fitting the model to data. The model has only one dimensionful parameter, h0, and by the sum rule that we saw, the only value that lambda can pick up is of order h0 square. Of course, it could be 0 times h0 square. If you made precise measurements and really made them very, very well, we might deduce that lambda is actually 0. In fact, our sensitivity is not that big. I claim our sensitivity is just of order h0 square, plus minus 1. So it could be 0, it could be twice, but it's of that order. And that is the thesis that I'll extend later in the talk. So let's go back to this cosmological principle on which this standard cosmology is based, and this is the man who propounded it. In fact, I learned recently that he had hosted Einstein when he gave his Rhodes lectures in Oxford in 1932, 3 years he visited, and sorry? That's right, yeah. But the foundation paid for it, I think. Anyway, Mill chaired the lectures because I heard from his daughter, who in fact now lives in Hull, that they had them to dinner and they met the great man and all that. And it would have been very interesting to hear what they spoke about, because Einstein was then, in the lectures, he actually presented a bouncing universe model. And he wrote down a formula for the radius, which is wrong by a factor of 100. It is preserved in a blackboard in our Museum of the History of Science. But anyway, he said the universe must appear the same to all observers, which is, of course, an extension of the Copernican idea that there is nothing special about us. So from being the center of the universe, we have decided to demote ourselves entirely. Fair enough. And as I have also mentioned earlier, at least we know that this is not the case for where we are in time. That was the so-called perfect cosmological principle, which was the basis for steady-state cosmology, but that was ruled out by observational data. But we have continued to cling to this Copernican idea, and there are lots of papers in cosmological journals where people rage against the idea that we might drop the Copernican assumption. Actually, you have already dropped it, and anyone who studies the cosmic microwave background is familiar with the idea that we don't understand why, for example, the low multipoles in the microwave background are anomalously low in amplitude, and the explanation given for that is cosmic variance, which is really accepting that we are not really just about, we are at some particular random point in a Gaussian random field, and from our vantage point, we don't see a quadrupole or a octupole. So when convenient, we do drop the Copernican principle, but otherwise people are very precious about it. So my point is the following, that we have had a lot of very impressive surveys, Planck and the Sloan Digital Sky Survey. I've showed you the results, and that have given us this universe which is supposedly dominated by dark energy, about depends on the numbers, vary between 2/3 to 3/4. And there are forthcoming missions like the Large Synoptic Survey Telescope, which is under construction. This is Euclid, the satellite that will fly quite soon, which will specialize in lensing. This will do a survey, full sky survey, and these are very impressive missions that are coming up. But somehow, if you look at the blue book or yellow book or whatever physics case that these missions have, they're all focusing on parameter determination of lambda CDM, like the model is proven beyond doubt. And it's true that there is now a standard cosmological model, but I have put it in quotes and I put it in lowercase because this is not the same as the standard model of particle physics, which is a capital S and a capital M, because there the underlying assumptions have been checked, have been tested, they have been verified at the quantum level. We have measured the loop corrections to it at LEP. And we know that the standard model should really be, well, you've heard about it in previous lectures, you know that it's really like standard theory. It is not really a model. We are fairly sure that the model is correct. Here, model selection has not been indulged in for some time. People are convinced this is the right model. I'm not so sure. So if I look at some, Google isotropy of the universe or something, I'll get the hit on Wikipedia. It says data from the Planck satellite show the universe to be isotropic. Here is the picture that they show. Anybody who works on the CMB will first of all know that this is not really how the sky looks. There's a huge band here which is due to our galaxy, which has to be subtracted out. This part is completely fake. You can't actually see that part. It is simulated data which comes in that band. Be that as it may, it looks fairly isotropic, and when you take the power spectrum of that, which assumes that it is isotropic, then the 2-point correlation suffices to describe it if the fluctuations are Gaussian, and on that basis you can construct a power spectrum which is the Fourier transform of the 2-point correlation, and that has this characteristic peak at a degree which was precisely the causal angle on the last scattering surface I pointed out where the light cones just touch. And of course you expect most of the astrophysical activity to happen on that scale, and indeed you do. And then there are subsidiary peaks, because what you're really seeing is a snapshot of a wave in the coupled baryon photon fluid at last scattering. And I pointed out in one of the lectures that we are very lucky that this transition was so sharp. Otherwise it would have been smeared out. You can see it getting smeared out. This is called silk damping, but it is not so abrupt. You can see 5 or 6 peaks, and these are proved to be very useful. So we are supposed to see this, okay? Now, and that is very important, because then we have this beautiful picture of how those fluctuations would have grown in the sea of dark matter that dominates the universe to create this large-scale structure of galaxies that we see today. And we don't know where these fluctuations came from. We have some framework called inflation in which you can get the required scale invariant structure. We cannot predict the amplitude. That has to be necessarily fine-tuned. Even getting the scale invariance is not easy, but you can construct toy models in which that happens. But let us recall that Harrison and Zeldovich had predicted years earlier that you should have just such a spectrum from purely general grounds, nothing to do with inflation. Otherwise, you would have either too many black holes or too large anisotropies. But nonetheless, this scheme works very well, and obviously we can believe that we have understood from first principles how the large-scale structure of the universe was created, right? This also, by the way, is the strongest argument for dark matter, because between here and here is just a factor of 1,000 in redshift, and Lifshitz taught us that fluctuations grow proportional to the scale factor in an expanding space-time. So they could only have grown by a factor of 1,000, and that is not enough to take these fluctuations and make them into this, structures that are going nonlinear. You need the fluctuations to have started growing earlier than last scattering, a factor of 10 or so earlier. So you needed the universe to have become matter dominated 10 times earlier, and so you need some component that doesn't couple to the photons, which could have supported the growth of the perturbations without them being washed out, right? Now, this picture I've shown you before, that all this is based on the idea that everything is isotropic and homogeneous. But if I look at the sky, I don't see isotropy. I see a prominent dipole in the cosmic microwave background with this is 2.726 degrees Kelvin, but this is about 3 milli-K stronger, and this is 3 milli-K weaker. And in fact, the temperature pattern is nicely fitted by this formula, which you'll recognize as the expected temperature variation for an inertial observer who's moving with a velocity beta with respect to the frame in which this radiation is truly isotropic. So this is interpreted for that reason as our motion with respect to the frame in which the CMB is truly isotropic. It's a kinematic interpretation. I emphasize interpretation because you don't really know if that is true. We have not seen. One way to test if it is true would be to measure the so-called aberration of the CMB. Now Planck tried to do this, but Planck did not have the sensitivity to measure it. Okay, what they found was consistent with it, but the effect is too small to be measured by Planck. Perhaps a future mission will actually measure the aberration, which is a very old subject. You know, Bradley, who was Astronomer Royal at Oxford, I think he talked about it back in the 18th century, right? And he measured the speed of light using it. Now, the motion of the local groove, which is our galaxy, Andromeda, large Magellanic clouds, etc., is actually faster because the sun is in fact moving in the opposite direction around the galaxy, so the two velocities add up. And so our local group is actually moving at this velocity towards this direction. Now, we believe that this motion is because of some local inhomogeneity, right? That's pulling us. So there is local inhomogeneity because, just one second, because for example, Andromeda is actually not going away from us in the Hubble flow. It is close enough to us as to be under our gravitational attraction. So you expect there to be local departures from the Hubble flow, which will cause streaming motions, but they should die out when you go to large scales. And that scale on which they should die out should be of order 100 megaparsecs. And in fact, I showed you that counts of galaxies in Sloan's Digital Sky Survey and this survey are supposed to be scaling as R cube, in other words, homogeneity, on scales larger than 100 megaparsec. Yeah?
So this is the way that we calculate the velocity of our local group?
Yes.
Isn't there any other way to calculate the velocity and then compare it to this? I mean, by looking at the nearby galaxies.
No, but you need, as somebody famous said, you need a place to stand on before then you can measure the world. So you have to first build a frame of reference. Yeah. Our frame of reference is heliocentric frame of reference, right? Based in the solar system, right? And then we measure the velocities of local objects, right, which have different vectors, and then we add them up together with reference to that frame. There is no independent way of measuring velocities because the only things you can measure are things to which you know the distance independently. So these are objects to which you know the distance independently using Cepheids or whatever. We are not using redshifts. You cannot use redshifts to measure distances when you are testing the idea that the redshift is cosmological or not.
Yeah, but what if we calculate our velocity with respect to the center of our galaxy and then...
How do you do that?
You cannot even do that?
Well, think about it and then I'll carry on with my lecture. If you could do that, then you'll be home, right? So, if we map out the distribution of matter in our neighborhood, we are here at the center of the picture, and I have shown you, astronomers have mapped it all out. This is the Virgo cluster, we belong to that. In fact, we are infalling towards the center of Virgo, but the whole thing is moving coherently, as I'll show you. We are moving in this direction towards the Shapley supercluster, and I've drawn for your convenience a 100 megaparsec radius ball to indicate that this is the scale on which the universe is supposed to become smooth and homogeneous. I leave it to you to decide whether that's how it looks to you. Of course, this is somewhat superficial because this is showing where the galaxies are. What really matters is where the dark matter is, because that is 6 times more, right? And we cannot map the dark matter in these pictures. You can only map dark matter by gravitational lensing, and that does not give us a picture like this over this kind of scale, which is 600 megaparsec. Now, the point I just want to make with this picture is that we are not actually co-moving observers. This is assumed in all interpretations of data. Sometimes corrections are made for this local peculiar flow, but rather superficially, as I'll show you. And therefore, your whole belief that we are in an isotropic universe in which we are seeing everything as isotropic because we're in the frame of reference where this is so is simply not the case. Okay. Now, just a little, try to avoid equations for this lecture, but just a few to show you that it's all very sound, very pakka. Okay. So imagine there is some density contrast, which is just the density minus the average value over the average value. Then you can ask how it evolves with time in an expanding universe. This is the usual Poisson's equation in an expanding universe. And for those technically minded, we are looking at the growing mode solution, not the decaying mode, obviously. And the point is that the density contrast grows the directions of everything remains the same. There is no vorticity in the problem. So the gradient of the potential is in the same direction, and the direction of the acceleration, and of course its integral will be the peculiar velocity, they all remain unchanged. You can't deviate from the direction. Now, the peculiar velocity field is just the Newtonian formulation is just the Newton's force law, which is written here. This is the 1/r² force law in terms of the density excess, and that will tell you what the velocity is according for the Hubble flow. So the peculiar Hubble flow, which is the difference between the actual flow velocity and the value that you should have in an isotropic universe, this would be technically the trace of the shear tensor. We are really trying to find the shear tensor, is then given by this integral, okay, so where you are integrating over this density contrast, which gives you this corresponding velocity, and you put the velocity in there. And actually, when you do this in a real survey, you have to use some kind of a filter function. So that is just a technical point. For example, if your survey is volume limited, then you would typically have a window function which looks like that. It's like a top hat or a step function or something. And so that's why that is put in there. Okay. Now, we really like to work in terms of in Fourier space where things become much simpler. So when you take the Fourier transform of the density perturbation, you expand it in plane waves, and then you can look at each mode in wave number one by one. They are orthogonal, and then you can write the Hubble parameter contrast in terms of the same quantities, except now we are in Fourier space where the Fourier transform of that top hat looks like that. And we can then ask an important phenomenological question: what sort of fluctuations would you expect in the Hubble constant, the variance of the Hubble constant from point to point in an universe which has a power spectrum of fluctuations characterized by some P of k, the power spectrum. Okay. Now, this is because we know the growth rate of the fluctuations from the theory of gravity, and we can calculate this. And interestingly, this is the fluctuation of the Hubble parameter. So you can see that it can be of order 10% on scales of 1020 megaparsec. This is 10 megaparsec, 20 megaparsec. It's actually h inverse, so you have to multiply it by 1 over h. But if you go to larger scale, say you go to 100 megaparsec, it has already dropped to about 1%. And interestingly, these two curves are for two very different choices of the power spectrum. It doesn't actually matter what the power spectrum is because you're integrating over the whole thing. So even if I put a spike in the power spectrum at 100 megaparsec, it will be smeared out by this kernel. And this is pretty insensitive, as I said, to the power spectrum. And this is, for example, the peculiar velocity expectation. It should have dropped. This is in units of 100 kilometers per second. So by a couple of 100 megaparsecs, it should have dropped to 100 kilometers per second or so. Now, let's look at the data to see if that is actually true. And one of the things you can do with the data, that actually thanks to the supernova people, we do have some data, is we have maps of the redshifts of the galaxies that host supernovae, right? And what we've plotted here is whether the data points have a distance according to what you expect in an isotropic universe, or they are more or less. Okay, so the green spots are those with the magnitude which is less than the expected value, and the red spots are the ones which have greater. Actually, lambda CDM is really a misnomer here because this is so close that the expansion is basically free expansion. There is no effect of lambda yet. but we are really testing for isotropy. Now, when we look at this data carefully, we can sort of do tomography. In other words, we can take shells of redshift and ask for where the dipole is as we go out in redshift, and the residuals that we'll find would be the peculiar velocity. Okay? So when we do this exercise, and obviously you have to make lots of systematic checks to make sure that we are not biased by the fact that the sky coverage of the supernova is very non-uniform. So you have to develop a statistic that is robust towards incomplete sky coverage. This is a real problem in cosmology now. Nobody worried about it because the assumption is everything is isotropic, so who cares which direction you're looking at. But if the universe is anisotropic, it makes a huge difference. So this is the dipole that we infer from the supernovae in this redshift interval, or in the top redshift interval, which is here. So to give you some sense of the distance, that corresponds to a distance of 260 megaparsecs. Okay? And of course it's linear. This black dot is the direction in which you're moving through the CMB, which is pretty well known. Within uncertainties, we are moving in the same direction, the peculiar flow, right? And therefore, we can read off the peculiar flow. These are these black points, and they are systematically above the expectation from the standard Gaussian random field isotropic assumption. So the error bars are very large because we are honest about the systematic uncertainties. So this is nothing to write home about, but you notice that they're all on one side. So a better measurement would be able to tell us whether or not there really is a discrepancy with the expected flow in the standard cosmology. Other people had earlier found the same thing using optical galaxies, which extended out somewhat closer. We have gone out to the Shapley supercluster, that is 260 megaparsec. We find there is no convergence to the CMB frame as you would have expected, even at a scale which is nearly 3 times the alleged scale of homogeneity. However, nobody took this seriously because these error bars are very large, as you see. But now the 6-degree field galaxy redshift survey, which has now looked at 11,000 galaxies, and to come back to the question you asked earlier, these galaxies have their distance measured not by the redshift, but by using something called the fundamental plane relationship, which is some empirical relationship for elliptical galaxies, which allows you to figure out what their intrinsic brightness is from looking at the galaxies themselves. And using that, that's actually good to about 15% calibrated by Sloan data. And using that, these guys have measured the velocity now. This was our measurement with the huge error bar, right? And there was another measurement by the nearby supernova factory, which extended our result beyond to about 300 megaparsecs. They went out to the Sloan Great Wall, velocity field still carrying on. And you can see that compared to the expectation for the standard model, which is shown by this black line or the dotted line according to which filter you're using, there is a clear discrepancy now, right? Now, previous measurements have been rather muddled, and small scales there is agreement, but there clearly is increasing divergence of what's going on. On very large scales, Planck can set an upper bound using the Sunyaev-Zeldovich effect in clusters, and there was a question about it earlier in a previous talk about a alleged dark flow, which would be at about 700 kilometers per second up to about here. So Planck claims to constrain that in its lowest bin, but Planck cannot actually come to any smaller scales than this. But the reality of that very high flow is still disputed. These are the people, this is from, a bunch of astronomers at the Anglo-Australian telescope who have no axe to grind like me. I've stated my prejudice already. They find that this is indeed the case. Now, you could ask, how often might you find yourself in a Gaussian random field in a location where just by chance the velocity happens to be much bigger than the expectation? There is some probability for that. Well, we interrogated these dark sky simulations, and after wasting a lot of CPU time, we established that it is less than 1%. If you ask, how often do observers like ourselves, in other words, inhabiting a galaxy of our mass with neighbors like we do, have this coherent bulk motion, then that number is less than 1%. In fact, really much smaller than 1%, but we are running out of statistics at this point because you're looking at the tail of some distribution. There are not that many such locations, even in the dark sky simulation. So in other words, we are very rare observers. So this is to substantiate that in the standard picture, then at least you'll have to agree that that measurement tells us that we are very rare observers. Now, what sort of implication might this have? So Christos Sagas, who is a relativist at Thessaloniki, he has been writing papers for some years pointing out that if you're in a patch of space-time which is moving coherently rather than expanding with the Hubble flow in some direction, then we are so-called tilted observers, a terminology that was introduced by Ellis, George Ellis, not John Ellis. And in that case, you can have a situation where the mean peculiar velocity of this patch can interfere with the measurement of velocities of objects which are outside the patch, such that you might have a deceleration parameter inferred from the data which has to be corrected by what this patch is doing, and this is the opposite sign to the one that you would infer from the observations of objects here, and indeed that would allow you perhaps to infer a negative deceleration parameter when it's actually positive. Okay, this can happen. Now, interestingly, as I'll show you later, over 3/4 of the measured supernovae are within this patch, right? So we are observing objects which are within the same bulk flow that we are in. That you can see from this here, which shows the distribution of the supernovae on the sky. So these 4 green points here are the SNLS survey. They occupy redshifts between around 0.1 and about 1, right? This is a recent survey. The Sloan Digital Sky Survey is that little strip there that bridges the gap between 0.1 and 0.3 or so. The red points, which are about half the sample, they are at very low redshift, right? They're very local. They're distributed all over the sky. And there are about a dozen supernovae which are measured by the Hubble Space Telescope, which are also in some particular directions, but they are so few in number they don't really matter, right? And this is the galactic plane. Obviously, you try and observe away from the galactic plane. Now, this has got 740 supernovae, and they have been analyzed by this collaboration, but when they fit the data to the model, they actually assume that the model is lambda CDM, and they adjust the error bars to get a fit with a chi-square of 1 per degree of freedom. In other words, what they're doing is not model selection, they're doing parameter estimation. This is not hidden, this is declared in their papers. So we don't do that, we apply a principal statistical analysis, maximum likelihood. And before that, let me tell you briefly what's going on with supernovae. So they are meant to be thermonuclear explosions. We don't actually know exactly how it happened, maybe a binary system, maybe a little one compact object accreting from a massive companion, but basically they go boom at some point, and you can observe them in different filters, different bands, and they have specific names in the astronomical literature, who then astronomers measured the magnitude, which is the log of the intensity of the flux. And the real advance that has been made is that with these light curves, you can measure the rise of the light curve. Now, just stop to think for a minute. How did the astronomers know that this guy was going to go supernova? It's just some star in a galaxy. Well, they didn't. They look at the same patch of sky again and again every night, and if a supernova goes off, you can go back and look at the plate 2 weeks earlier. And that's very important, because then you can know the width of the light curve. And if you know the width of the light curve, you can do the following. If you just plot the supernova light curves, they're all over the place. But if you follow the suggestion of Phillips, who pointed out that there is an empirical correlation between the peak magnitude and the width of the light curve, then you can use this empirical correlation, which is slightly different in different bands, to standardize this huge scatter. Remember, this is a log scale, right? So this huge scatter you can reduce to a manageable scatter, so that you can actually use them as standard candles by using that correlation, which is empirical and certainly not understood theoretically. In fact, a colleague at Oxford who does the theory told me that people had predicted the opposite slope for that correlation. So they really don't understand it. But what they then do, this is the SALT 2 method. This is spectral adaptive light curve template, okay, model version 2. where you observe some magnitude and you correct that by a stretch factor and a color factor, which is essentially doing this exercise that you are seeing here in order to standardize them. M is the absolute magnitude of the supernovae, which is what you are after. But you don't know that. You consider that they really are standard candles. You're seeing all these fluctuations. So, yes?
Isn't the process of supernova due to deleptonization?
Yes, you can have other mechanisms. So here the assumption is that they are all thermonuclear explosions. If there was some different mechanisms, then you would expect a huge scatter. Indeed, you see the scatter. So maybe the points that did not fit here, like this guy was such a supernova, which, there are always weird objects which don't fit. That's another worry, that you might, unless you can get a good spectrum, you don't really know what was the object. And even when you get a spectrum, you talk to a supernova astronomer, they'll tell you that they have a hard time identifying, especially when they're quite far away. So these guys then publish a chart for the first time in 2014, which tells you the redshift of the supernova, the magnitude that they measure, and these correction factors, the stretch and color corrections. They also tell you the stellar mass of the galaxy that the supernova is in. We didn't actually find that any correlation with this, but that could be correlated with something else. It could be correlated with whether the thing is in a spiral arm or not, or who knows. Basically, this is the simplified model that is adopted for the standard analysis. Now, once you measure those quantities, you can use the equations that I described in some lecture on how the luminosity distance determines the cosmological parameters. And basically, from the observed magnitude, you can then work out from the magnitude luminosity distance relationship, you can work out what these cosmological parameters are, right? Actually, you don't really need to do that for the deceleration, because that's a kinematic quantity. It doesn't require a model. You just do a Taylor expansion of the luminosity distance in terms of the Hubble parameter, the deceleration parameter. You can go to a third derivative. This is called the jerk for some reason. And then there is another term that is called the snap, and so on, okay? But if obviously this expansion is only going to be good for z smaller than 1, but we find actually the luminosity distance from this expansion agrees with the exact distance to within 6% for all the supernovae that have been looked at so far. So it's good enough. And then you construct a maximum likelihood estimator, which is the probability of the data given a model, right? And what you can do is you can factorize that into something that depends on the supernovae and something that depends on the cosmology. I think it's a reasonable assumption that the supernova and the cosmology are independent, right? And what we observed, or my master student Jeppe Nielsen observed, is that if he just took the data and he plotted the stretch and color corrections, they actually are reasonably well fitted by Gaussians. Okay? So, I mean, not perfectly, but good enough. What that means is that these likelihoods, individual likelihoods that depend on the supernovae and the cosmology, these distributions, if we say that the observed stretch and color distributions are drawn from underlying Gaussians, which are described by these distributions, then I know how to integrate a Gaussian. I can calculate these likelihoods analytically, okay, in terms of everything in terms of observed quantities. So Alberto Gufanti, who joined us on this, is an expert on statistics. In fact, he was involved in analyzing the neural network PDFs, and we are actually discussing how to apply neural networks, but then the thing turned out to be even simpler. We didn't need to do that. So then we can construct a likelihood. For lack of time, I'll skip all these equations. It doesn't matter, just to let you know that we know what we are doing. And when we construct the likelihoods, we find that the 1, 2, 3 sigma contours of the usual banana in omega lambda versus omega matter is not up here as is usually shown, but it's actually down here. Okay, and there are 10 parameter, if I do a 10 parameter fit just to compare with the usual thing, then this is what happens. Now at this point a lot of people say, but we know that omega matter is more than 0.3, so you can't even go down there, you should be up here. We are actually showing this just to show that the previous statistical analysis by the supernova people was not principled. Okay, this is a correct way to treat the data, not assume the answer. So that is the only point of this plot. Don't try to read more into it, right? And as I've said, this is our result was reproduced by another group at Imperial College who have a Bayesian approach, and they use the same likelihood. And in fact, the co-author, this is Roberto Trotta and collaborators, and their co-author is Van Dyke, who is the head of statistics at Imperial. So, we are quite sure that our statistical treatment is absolutely sound. Now, something much more interesting that has happened very recently is that we have just analyzed the JLA catalog in the light of our finding that there is a bulk flow and that the JLA objects have not been corrected appropriately for the bulk flow. We in fact look to now see if there is possibly a dipole in the deceleration parameter. Okay? So in other words, we allow the deceleration parameter to have a monopole component, isotropic, as you would expect in the standard cosmology, plus a dipole component along some direction. And lo and behold, the maximum likelihood estimator, this is unpublished by the way, this is a version of this is in this archive paper. We find that there is a dipole which is huge, which is of order 6 in these units. And there is also a monopole, but the monopole is in fact consistent with 0 now at something like 1.8 sigma, whereas the dipole is non-zero at 3.9 sigma. Okay? Now this is very interesting because what this says is that rather than the debate being whether the universe is accelerating or decelerating, so this contour tells you that it is likely accelerating, but it could also be decelerating with a reasonable probability. 1.8 sigma is not really that strong, but much more likely there is an anisotropy, that is to say the deceleration or acceleration is most in the direction that you are moving through the cosmic microwave background, right? That surely suggests a local effect. It cannot be a global effect because if it was really due to lambda, then it would be uniform over the sky, right? And it is not so. The data is saying that it is not so, right? Now, that is why we believe that this cosmic acceleration is just an artifact of the fact of our being located inside this bulk flow. And as I mentioned, that includes 3/4 of the observed supernovae. So now we really have to start asking questions like, when somebody claims any result, which part of the sky did you look at? Did you look in the direction you're moving through the CMB or orthogonal to it, or in the opposite direction? And you might be interested to know that both the supernova cosmology team and the High-Z supernova search team, the people who got the Nobel Prize, they looked at 45 supernovae opposite to the direction that you are moving through the CMB. So, people can find different answers according to which part of the sky they're looking at, if this is true. Now, you might at this point say, okay, but don't we have independent lines of evidence that there is acceleration? Like, don't we know that from the baryon acoustic oscillations? Don't we know that from the growth of structure? Don't we know that from gravitational lensing and so on? So a colleague of mine, Alain Blanchard, who is at Toulouse, a distinguished astrocosmologist, he wrote to me saying, I've always had doubts about the supernova data, but the baryon acoustic oscillations, that nails it. So I said, have you looked at the data? He says, no. I said, well, look at the data. So he has looked at the data, and what they show here in this plot is that whereas lambda CDM does fit the baryon acoustic oscillation data very well, a non-accelerating power law also fits it very well. Okay? NALPL stands for a model in which the scale factor is going as t to the 0.92, in other words, very close to uniform rate of expansion. Why is that? That's because the baryon acoustic oscillation measurements have not actually got enough statistics yet to detect the BAO peak, which is a 1% change in the correlation function at a intergalaxy separation of 110 H inverse megaparsecs. To measure that at 5 sigma, you need about 6 million galaxies with spectroscopic redshifts. So far, we don't have more than of order 1 million. People have tried to bump up the numbers by including quasars and so on, but then that induces lots of systematic effects, biases, the selection function is not flat and so on. But this is the proof of the pudding. If that data was actually proving acceleration, then it would fit that model, but not this one, but it fits both. There are other pieces of evidence, for example, the growth of structure, and here the green line is the non-accelerating power law expectation, the red line, the blue line which is under the red line is the lambda CDM expectation. the data you can see are certainly not of good enough quality to tell the difference between them. And the same goes for sigma 8, which is something that describes the variance of density fluctuations in an 8 H inverse megaparsec box, that being the scale of clusters of galaxies. So this is a well-known measure of the clustering of clusters of galaxies. And again, the data is too bad, not good enough, sorry, to distinguish between the two things. And for the supernovae, of course, as I've already explained, that you can't tell the difference, right? So this is the best fit for this data. Now, what about the CMB? People say that the CMB surely has established everything, and indeed there is massive advance in the CMB starting from that fuzzy picture of the fluctuations that Kobe produced. In this map, incidentally, for your interest, half the fluctuations that you see on the sky were actually instrumental noise. The signal to noise was 1. So it was actually very brave of them to have claimed to have detected it, but they were right. They were there, and they showed up, of course, very well in WMAP and even better in Planck down to small scales, right? So massive advance in the field. The power spectrum looked like that in the Kobe days, and in WMAP already you are seeing lots of interesting features. You are seeing, but you notice also some other interesting features. There are points here that don't fit on that line. So this is a glitch, as they called it, at multipole number of 22, where there is far less power than you would expect from the rest of the model. So generally speaking, this kind of way of plotting the data essentially maps 1 degree and sub-degree of the sky into most of the plot. These correspond to large-scale features, quadrupole, octupole, etc. They are all below the expectation. There is basically no power on the sky for angular separations more than 60 degrees, if you look at the angular correlation function. That is, as I said, usually explained by cosmic variance. So it is not that we are strangers to the idea that we might be in a special spot when convenient. And the same is, of course, true of Planck. Planck cannot fight cosmic variance. It can only measure this small scale structure more precisely. You have the same discrepancies here, right? These points here. Now, we know, I've already described what these things are. You know that what CMB people do is that they expand the sky in a set of orthogonal functions. And this is, for example, then the monopole, quadrupole, octupole, etc. And then you plot the power in them, right? And for each L, you have 2 L plus 1 independent measurements. So this is the average value. And you can see this is from WMAP, but something very similar from Planck. And this peak, as I said, corresponds to the size of the causal sound horizon, which is almost the light speed at that time. It's a relativistic fluid nearly on the last scattering surface. Now, the lack of power which you saw in that is very striking. So if I plot the 2-point angular correlation function from the data, that is that line there, okay? This is from WMAP. Planck has not published this plot, but it will be very similar. And the expectation of the standard model is that line there, okay? But there is a huge cosmic variance which is indicated by the shaded band. Why is the cosmic variance increasing? Because, as I said, for any L you have 2 L plus 1 measurements. So obviously for low L you have very few independent measurements. The uncertainty is very large. And it becomes huge at 180 degrees. So you might say that what you observe, the blue line, could be a fluctuation of what you expect, namely the black line. And indeed, if you calculate what that is, the probability of that happening is about 2% or something. It is not, it is small, but it can happen. 0.2% is not too bad. But that is not the end of the story. If you look at the low multipoles, you actually see things that you don't expect. These are meant to be randomly oriented on the sky if you really have statistical isotropy. But in fact, the plane of the quadrupole and the octupole are beautifully aligned, okay? And if you ask what is the joint probability for this happening as well as them having low power, it depends on what question you ask, what answer you get or how. So Max Tegmark and company looked at this and they said, now that is unusual. That is at the level where you start taking notice, okay? Now, at this point, you say, look, what can we do? This could be due to a variety of reasons. The way the foregrounds are subtracted could have led to this kind of alignment, or, but basically, you can't do anything about it. It's not that you can build a better satellite or a better mission and get a better measurement. This is on scales where that will not help you. So this has remained an unsolved problem. Meanwhile, we have been doing something different. We have been trying to take the data to unfold it to get back to the primordial spectrum of fluctuations, which is usually assumed to be a power law. Now, you do expect a power law from toy models of inflation, but they are not physical models. I do have no reason to believe that they are the truth. So I think this should be done empirically. And when we do this, we use a technique called Tikhonov regularization, which is actually introduced by a man called Tikhonov, who was a hero of the Soviet Union, because this is used for image processing. Okay? Using this, you can analyze a fuzzy photograph taken from a satellite or a plane, and you can see what is actually there. Now, Tikhonov had an advantage over us because he knows when he gets the answer, it looks like a tank or a battleship or whatever. We don't know what the primordial spectrum is supposed to look like, so we don't have the same advantage of knowing when to stop. So I'm just saying that we are not as good as Tikhonov regularization, which is well known in image processing. So we have to use a certain regularization parameter and tune it so you don't amplify the noise too much, and nor do we wash out features that are actually there. We believe we have done the best that can be done, and the spectrum that we get is shown inside these bands. Okay, and this is the power law that is quoted by the experiments. They quote some power law with some index plus minus 0.02 or something. But actually that plus minus 0.02 is not very meaningful, because you can see that actually the data, while it can be described by a power law, does show deviations from it. They're not individually significant. There's only about 2 sigma, but it is clear that you cannot argue that the data is a power law. You can only say it is consistent with the power law. This framework is useful because it includes not just Planck and WMAP and polarization, but also galaxy surveys. It includes lensing, it includes Lyman alpha, which improve the reconstruction on the small scales. Now, just to tell you about the pitfalls of this business, that peak there, which is at L of, I think, 1260 or something, that looks very significant. And we thought it was very significant until Raphael Flauger, who works with David Spergel, he told us that they thought that it was due to some pump on Planck, which caused a vibration of the spacecraft, which the observers had corrected for, but not in the 238 gigahertz channel. And they thought it might have something to do with that. And actually they were right. When you took out the 238 gigahertz channel, that peak dropped. So just to warn you that in this business, a vibrating pump can imprint a feature on a primordial spectrum. So you have to be very cautious. I'm not expecting you to take this literally, but just to tell you what the state of the art is. Because that brings me to my last topic, for which I'll just take 2 more minutes if I may. So this is some work that we have been doing more recently, following up the suggestion or the framework that was presented by Hajian and Saurodeep, which is that the power spectrum itself may not be isotropic. It might have a built-in anisotropy, which would of course be a signature of whatever process created it. And you could think of ways in which this can happen. So here, therefore, we have the usual isotropic power spectrum, but then we can expand the anisotropic power also in angular spherical harmonics. And we focus on the quadrupole modulation because by symmetry, this L has to be even. And we then define these coefficients. Just keep an eye on what this terminology is. So we are looking at these things. They are called BIPOSH, for bipolar spherical harmonics. And we did a full analysis. This was done with Amil Durakovic, who was my student in Copenhagen, Paul Hunt, my collaborator on the spectral decomposition, and Shubhadeep Mukherjee, who was a visiting summer student. He was Tarun's student, right? And other people have also looked at it earlier. And what they could not do, which we added to the game, was the ability to look for a wave number dependent modulation. So people had only looked for a constant modulation, and they had set limits on it. They had not been able to find anything. And we do this using the Planck data release, and in fact the covariance is from the full focal plane simulation. So this is state of the art. You can't do better than this. When we do this, I told you about keeping an eye on those G2 coefficients. So those coefficients which determine the modulation are plotted on the vertical axis versus the wave number. And if there was nothing, if everything was isotropic, then they would all be consistent with 0, okay, here. So you can see that they are not consistent with 0, they do deviate from 0. Now I don't have time to explain to you all these uncertainty bands that you have plotted here. This is directly from the data and the Planck simulation. So we have every confidence that they are right. So essentially the bottom line is that we do find a deviation from isotropy, but it is only 2.1 sigma, okay? However, if we consider a test statistic that is not only looking at the amplitude of the modulation, but also the directions, okay, then the fact that all these things are correlated in direction means that the significance of a departure from isotropy goes up to 6.9 sigma, okay. It's extremely unlikely to happen by chance. Now, this was published last year in JCAP, and I know that the Planck people were now trying to reproduce it because their own analysis did not have this dependence on K, which we are able to bring in thanks to our ability to deconvolute the spectrum by this Tikhonov mechanism. So when we put this on the sky, we see something interesting. Earlier, Hans Christian Eriksen, who is on the Planck team, had found that there is a hemispherical modulation in the CMB as if modulated by a dipole, and that has a specific direction in the sky, right, around down here. The CMB direction is up here at 90 degrees, right, and they find it in every wave band of WMAP. It's also been now found in Planck. So this thing is there at about 3 sigma level. Now when we ask what is the direction of our quadrupolar modulation, so there is a hot spot and a cold spot, and we find that this is the CMB direction, this is the direction of the hemispherical asymmetry, and the modulations that we find are at 90 degrees to both of them, okay, for the hot spot direction. I mean, within uncertainties, I mean, you find 97, but you know, this is all plus minus 10 degrees. So there's something very interesting going on. And this is something that, in fact, with more data, one will be able to test whether this is really there, because this involves two new techniques, one of which is known to the CMB community, but the other one, this deconvolution method, that has been done in a separate context, and the two have not been combined. So let me conclude, since I'm over time. There is a dipole in the recession velocities of host galaxies of supernovae. This result has been around now for 8 years. It has been confirmed by subsequent data from the nearby supernova factory, from the 6DF galaxy redshift survey, and it says that we are in a bulk flow which is stretching out to several hundred megaparsec, which is well beyond the scale at which the universe supposedly becomes homogeneous. So we don't really understand why that is going on. So the more surprising, or rather more radical statement I'm making is that the inference that the Hubble expansion is accelerating may be an artifact of our being located in this bulk flow, because there is a strong dipole in the inferred deceleration parameter aligned with the bulk flow, and the monopole drops in significance. So when we let our maximum likelihood estimator loose on the data, it tells us that actually the data is consistent with there really being a dipole and a tiny monopole, consistent with 0, okay? So that tells me that this is not a global thing at all. This is not a global cosmological effect. It's very likely to be a local effect. Then on top of that, we find there is a scale-dependent quadrupolar modulation of CMB anisotropy, and the direction is orthogonal to the CMB dipole. Now, I don't want to speculate on theoretically how this could be. You know, we can think in terms of isocurvature perturbations and so on the horizon scale, lots of complicated things. But generically, there seems to be some indication of something happening on the Hubble scale, on the horizon scale. That was already evident in the cutoff of the power spectrum on horizon scales, the suppression of power, and now we see it in these possible alignments. But that is something which is for future work. For now, all I would say is that the standard assumptions of isotropy and homogeneity should be scrutinized. And we have the tools to do that because there are forthcoming surveys, Euclid, LSST, the square kilometer array. They're all coming on. They will have the ability to provide us not 1 million, but 10 million, 100 million data points, redshifts, and so on. Measure gravitational lensing to measure distribution of radio sources up to millions, 10 millions. And so we'll, this is a common refrain. We'll always have definitive tests from the future data. But in this case, I hope I've been able to quantify for you why we need more data and just how much data we need. And most of all, what we need, I think, more than data, is open minds. And I hope that you will contribute to that. Thank you. Yes?
I'm sorry, I have a somehow irrelevant question, but it's too irrelevant.
No, do ask.
Yeah.
No problem.
I heard about a model that Roger Penrose published for the cosmology.
Yes.
You mean, please explain a little about that?
Well, I'm not very knowledgeable about that model, but as I understand, he believes there are hotspots on the sky which are evidence of past universes from which we have emerged, right? Now, these hotspots are on the CMB sky, so if I show you a picture of the CMB, it will become obvious what the issue is. Let me find a real picture of the CMB as opposed to these are all doctored pictures. So let's see. Okay, this is more of a real picture. This is the SMICA map, which is a galaxy mask, which has been applied to the Planck map. So in this picture, obviously with suitable contrast, Roger and his collaborators find spots which have a characteristic pattern and which are highly non-Gaussian, right? And they interpret in their theory. So the real question is, are there such patches on the CMB sky? Now, Roger quite rightly accepts the maps that have been published in the literature as a true depiction of the sky. Now, this ain't necessarily so, in the sense that to create a picture like that takes a lot of work. You have to subtract off galactic foregrounds, you have to correct for all sorts of systematic effects, you have to correct for the effect of that mask. There's something called apodization that happens to do that. And something that also is not very well known is that many of the pixels of the map making camera were affected by cosmic rays. So a lot of interpolation had to be done with the data in order to recover this. Now the net result of all that, what that effect would have had on any intrinsic non-Gaussian patterns is anyone's guess, okay? So the only people who can answer Roger's question are the Planck team themselves, because they did the data, right? We are doing what we can with the public data, but every experimentalist knows that what you provide for public consumption has to be cleaned up, okay? They do their best to clean it up in a way that doesn't bias it, but for subtle signatures like that, it's best to go back to the raw data. So I do not know whether Roger Penrose's claim to have seen such spots, it's certainly not been accepted by the CMB community. They do not say, yes, there are such things, right? As for the theoretical idea, of course, it's very interesting. Roger is a very inventive person, and but I cannot comment on that. Yeah?
So what about the possibilities to measure this hemispherical asymmetry by observing a large-scale structure? Because I will expect that there will be more structure on the southern hemisphere than the northern.
Yes, I see what you're saying. Now, actually, I happened to meet Shubhadeep in IIP last week, and he's working with Benjamin Wondelt on another application of these BIPOS harmonics. They've actually put out a paper where they believe they have another explanation of this dipolar hemispherical anisotropy, which would not imprint on large-scale structure. They think it is also something in the primordial perturbations, right? But it is true that empirically, to test the question, you could indeed do what you just suggested, see if there is a correlation with foreground structure. The problem is, well, for the benefit of others, basically photons from the CMB, when they come to us, they are of course falling in and out of potential wells, but everything cancels out a linear theory, okay? There's no effect. It's only if the potential wells are changing in time that you will see an effect. As for example, if curvature or cosmological constant comes to dominate, then you see this late integrated Sachs-Wolf effect. Here I would expect something more like a Riesz-Schama effect on very small scale. So you'd have to look on correlation in structure. So what sort of survey would you use to do this? I mean, galaxy survey? LSST, yes. Future surveys, yes. I'm saying currently I don't think you have any survey that would have the necessary. Yeah, LSST would be fine, because that is going to, you know, if it operates as designed, it's going to be really fantastic. And indeed, the real problem with the LSST is coping with the data. So just as well that particle physicists are running the show on that regard, they know how to handle terabytes or whatever of data. LSST will be a game changer, and I have been assured by some of the particle physicists involved in the LSST that they are going to do a blind analysis. The problem with cosmology currently, in my opinion, is that no analysis is done blindly. Everybody knows which lamppost to look under, okay? And one proof of confirmation bias in cosmology is that Rupert Croft, who was a guy who works on Lyman Alpha Forest, he looked at the literature and he found that in between 1998 and I think it was 2011, out of, I don't know, something like 35 measurements of lambda, right, not more than 2 of them were outside the 1 sigma band of the WMAP estimate, right? So if you wanted evidence that there is some confirmation bias, then there it is, okay? So you really should do blind analysis, but blind analysis is very hard to do. I mean, I'm on an experiment called IceCube. We do everything blind, okay? That's why we can believe what we find, okay? Otherwise, there is always a tendency to find what you set out to find or what you would like to find. And I think, actually, I certainly am not alone in saying this. Distinguished cosmologists have said that they really need to move to blind analysis, and LSST will do that. Yes?
Can you please open the slide where you compare the fits with the non-accelerating and accelerating model?
Okay.
Where they both were fitting very well.
Well, I had various, so you're talking about this one,
No.
then?
I think the ones with the lines
Yes,
from
yes.
different colors,
That's
in red, blue, and green.
One, two.
Flat lines fitting the baryon acoustic.
Oh, that one. You mean the Blanchard et al. Paper here? Yes.
Here, on the right top,
Huh.
why are the data points are moving with respect to each other?
Which data point?
For example, the one with the bigger error bar
Huh.
in the middle is moving with the one.
Oh, I see what you mean. Why that thing is moved. Well spotted. You're talking about this guy moving down here. Because this is actually, you have to look at the y-axis. This is the difference between the BAO observed and the BO in the fiducial model. The fiducial model is changing. So the deviation is also changing. So they're plotting it in a way as to make the differences obvious. It's the same data. Okay, and in this case it doesn't matter, because what you're looking at here is the growth of structure, and that is the expectation. The data does not have to be altered. You see, all this BAO data is obtained using a template. This is thank you for the question, because so a template means effectively in plain language that you expect to see a peak at a certain point, and you ask if the data is consistent with there being a peak there in the 2-point correlation, right? So the 2-point correlation sort of, it's something that looks like this. It's in fact not in R, it's actually in redshift space, but we'll let that pass. So this is the correlation function that is falling, and at a certain point there is a tiny little bump in that, okay? And this is at 110 H inverse megaparsec, okay? That's where this is supposed to be. Now, if you looked at 5 million galaxies, 6 million galaxies, you'd expect to see that, measure that at 5 sigma, right? You can work this out. In fact, somebody called Nyayesh Afshodhye, who is at Perimeter, he worked this out. However, the claim that was first made for this BAO peak was done with 35,000 galaxies. How can you do it with 35,000 galaxies? Because they did not actually answer that question. They answered the question, is there a peak at 110 H inverse megaparsec in this sample? And they said yes. That was in data release 3 of the Sloan Digital Sky Survey, DR3. Subsequently, a guy called Eyal Kazin at NYU, he looked at DR5 that had 115,000 luminous red galaxies. And he found no peak. Okay? So when I queried this, a prominent cosmologist who I'll not name wrote to me saying, well, everybody knows that in these small samples, there is only a 10% chance of seeing the peak because of cosmic variance. So 9 times out of 10, you don't expect to see the peak. It's completely understandable. But when you do see it, you can do precision cosmology with it, okay? So this is like saying that you take data at the LHC, you see evidence for something coming up in the 2-photon channel, you think that might be a Higgs, you take 3 times more data and the significance drops from 3 sigma down to less than 1 sigma. At that point, you would not say that this was just bad luck, okay? You might conclude that what you had seen earlier was a fluctuation. But the philosophy here is somewhat different. So we need to detect the BAO without a template. So bottom line, everything that you have seen, every publication has used a template. They have not actually looked at the data to see if the raw correlation function shows a peak. Yeah?
The Planck observation was made in space.
Yes.
So when you're sending a piece of electronic in the space,
Yeah.
well, it suffers a lot of
Indeed.
the thermal changes and
Sure.
charged particles and a lot of that stuff. So how do they all of them include some sort of uncertainty?
Well, as I mentioned in passing, Planck, the high-frequency instrument, HFI, did suffer quite a lot from cosmic ray bombardment. It was at Lagrangian point 2, and there is no magnetic field there. In lower orbit, the Earth's magnetic field still protects you. The cosmic rays are swept out. Nothing like that at L2. And actually, the cosmologists had not quite taken that into account. Fortunately, they realized how to deal with it after the fact, and in fact, the techniques that they developed are going to be important for every future mission. Yes, so they basically figured out a way in which to, as I said, interpolate between the data that they have to recover from the damaged pixels. Okay, I'm not privy to exactly how they did it, but they essentially saved the day after the fact. They actually corrected for this.
How long will it take to make this measure?
Well, the surveys are done in a matter of months. I mean, the Planck has been still up there, of course, but it stopped taking data several years ago. So it took several full sky pictures. It keeps scanning and it makes a full sky picture in a certain number of months and it does it again and so on. And then they do suitable averaging and so on to take out any artifacts due to the scan pattern, due to the change in the gain sensitivity. So, you know, that they have experience with. It was a very complicated instrument, much more complicated than WMAP, but that's what they had to do.
One last question. This direction of bulk flow that
Yes.
you measured with this EMB,
Yes.
does it correspond to any certain directions that we know about the local space around the instrument, such as the magnetic field or anything else?
No, it has nothing to do with the magnetic field of the Earth. It's in the direction that we are moving, it's in the direction of the Shapley supercluster. We know the direction, right? We can map out the structures in that direction.
Particular direction that we know of before.
Well, it is the direction of the Shapley supercluster. So, not that we walk around saying to people, oh, there is the Shapley supercluster. I've never seen it. I believe it is out there somewhere. But according to the astronomers, that's when they map out the distribution of galaxies, there is a concentration of matter there. However, and this was actually there in one of the plots, you do not see any infall it cannot be the shapely supercluster that is causing this bulk flow, because if so, then you would see an infall towards it when we look out. Where are we? Sorry, I don't have it in this talk here. You do not see any infall towards. So if you look at galaxies which are beyond Shapley, if Shapley was the responsible chap for pulling us, then on the other side they should be falling towards us. That is not so. They are also going away. So there is something even beyond Shapley. In fact, you need, I showed this in the lecture, you need a mass concentration of 10 to the 5 galaxies, 10 to the 17 solar masses, to account for the velocity with which you are moving from that, something at the distance. So the question can be posed another way. What are the odds of finding a mass fluctuation of 10 to the 5 galaxies, 10 to the 17 solar masses in the standard cosmology? And the answer is very, very low. Less than 1%. I already gave you the number, right? But that's not zero. And we actually, when you are looking at the tails of steeply falling distributions, it's hard to get accurate estimates, because a little mistake can put you exponentially up or down, right? So all we can say is that it is very rare. If people do a better simulation with more particles, etc., and actually on those scales, you start getting relativistic effects, so you should take those into account as well. But that has not yet been done. Essentially, this result that I mentioned to you, this is not even been published in a journal so far. It was shown at the Zeldovich conference 2 years ago. This plot here. Okay, this was at the Zeldovich Symposium in 2016. It has not yet appeared in a journal, right? Because, so when you talk to the guys who made it, I mean, they have published it, they've shown it publicly, and they're prepared to stand by it, because there is concern. I mean, peculiar velocities have always been very hard to measure, very uncertain, for the reason that you need direct distance estimators, and they're uncertain. But these distance estimators have been calibrated by the Sloan Digital Sky Survey, and they're good to 15%, okay, which is pretty good. The supernovae is supposed to give a better calibration, but they are subject to various other uncertainties, as I showed you. So I don't see anything, this is as good as it gets. But, this is still 11,000. It would be nice if it was more like 100,000 or 1 million even. That day will come. Yeah, please.
Where does this direction exactly point to
In the Earth. Okay. Well, all right. So let me show you the picture of the galaxy distribution. So we are going in this direction. Okay, we are moving in this direction. So if you take that vector back, and the precise coordinates I gave you earlier, the precise coordinates are these. This is the galactic longitude and latitude. Now, when it comes back in, where it points in the Earth depends on the time of day, because the Earth is rotating. So, but I mean, we know the direction on the celestial sphere. We can point to it, right? Now, this bulk flow direction is not as precisely known as the CMB direction. This is to plus minus 0.1 degree. But the bulk flow direction is not that well known. It's within 10 degrees, because, the data is too sparse. So we know it's something somewhere in that direction, but something is pulling us from beyond that, okay? And whatever that is something of order 10 to the 17 solar masses, at least. Yeah?
Maybe it's a somewhat provocative question.
Huh.
So if you allow yourself to drop the usual caution, so fantasize and speculate.
Me drop caution?
Yes, please. Just for a minute.
Yes.
I just wonder what kind of image of cosmos, of universe, replace this Copernican sort of picture if all of this will be confirmed in the future. So will we think of completely homogeneous cosmos around us, or what is the image that is in your mind?
Well, so I can tell you what people are thinking. So there is a guy called David Wiltshire in New Zealand. He was actually a student of Hawking. He moved to New Zealand later. His idea is that he is a relativist, but he's also started looking at data. In fact, we are corresponding about these things. And his idea is something called, what he calls the timescape picture of cosmology, which is simply to take into account that clocks run at different rates and different gravitational fields, right? So to him, inhomogeneities are like a map of how to construct a constant time hypersurface. In an isotropic homogeneous universe, it's trivial. You just draw a plane like that. But the real universe, it is not so. And his view is that what we are interpreting as dark energy is essentially due to not taking into account this timescape, as he calls it. Okay. Actually, I think he's saying exactly the same thing that other people are saying under a different guise, because the peculiar velocity, if you think about it, is nature's integration of density inhomogeneities. Okay. I showed you the equations. That is the response to inhomogeneities, whether it is in dark matter, visible matter, any kind of matter, we don't care. It's dynamical. That's why it is independent of bias in the galaxy distribution or whatever the hell it is. So effectively, I think we are talking about the same things, except that he has a formulation of how to calculate things in the timescape model. And that actually, again, when he analyzes the supernova data using our MLE, he finds that indeed there is no need for acceleration in his model, right? But the trouble with these models is that, that is something I alluded to earlier. In the case of the standard cosmology, we have this beautiful picture, okay? We have a story of creation from the very beginning till today, and one which is complicated. It's not trivial, but it is something that a smart graduate student today can completely understand, right? Now, this kind of pictures that I'm talking about, to construct a cosmology for them which is as ambitious as this, will be difficult. Because in this picture, we have little fluctuations, they grow under gravity, they give you this structure. There are some discrepancies, but on the whole, you do explain the large-scale structure. There are discrepancies. For example, I'll give you a very one that may not have been recognized as such, but is actually well known, which is that you heard of the bullet cluster. There are these two clusters of galaxies that have gone through each other at very high velocity. Now, you can ask, why do two clusters of galaxies on those huge scales, why are they going through each other? Why are they not going away from each other in the Hubble flow? I mean, isn't that what we are taught in kindergarten, right? And the answer to that would be, well, yeah, sure, but sometimes you have peculiar velocities, they can head towards each other. So you ask, what is the chance of that happening? And the answer is, well, more precisely, we ask the question, how many bullet cluster-like systems do you expect to see up to the redshift of the survey that found it, that was 0.3? The answer is, you expect 0.1 systems like the bullet cluster, where objects of those masses were initially approaching each other from a certain distance with a certain velocity and passed through each other a certain time ago, right? Now, you expect 0.1 and you see one, so, okay. Unfortunately now, or fortunately, astronomers being interested in such systems have started looking for them, and they've already found over a dozen. In fact, there are about 100 in the pipeline waiting to have their redshifts measured and to be put on a firm footing, right? So it seems to me that there are far more colliding clusters in the universe than you have any right to expect. So I would not say that the observations of large-scale structure are fully in agreement with what you expect from the standard picture. Having already admitted that on the whole it fits things pretty well, very well, right? But there are discrepancies. Now, the attitude is somewhat different. In particle physics, when everyone is looking for a discrepancy, everyone wants to find a departure from the standard model. In cosmology, I find it's just the opposite. Nobody wants to hear about any discrepancy. They want the thing to be perfect, okay? They get emotionally upset if you suggest that the number of clusters is perhaps more than you expect, right? I don't understand this because, seems to be a little insecure, to be honest. But I mean, this is a fact, that there is a tendency to guard zealously the standard model. Now, that might be because of what you are alluding to, that it is very hard to develop an alternative cosmology, right, which is as simple and tractable. But when I say simple, I say that advisedly because it is tractable, certainly, but simple. If you have got a lambda term which is of order h0 square, I don't find that simple at all, okay, because there is no explanation for it, and certainly no physical explanation for it. And I don't find any of the alternatives offered to lambda to be at all convincing. So I don't understand why we are trying to sweep the problem under the carpet. This is something that particle physicists have tried to answer and not succeeded in doing. But that's no reason to sweep it under the carpet, because the discovery of lambda, I think, was an accident waiting to happen. It has happened actually 3 times before, even in 20th century cosmology. It was going to happen sometime, because, you know, as the sensitivity grew. And I think we have to just ask the question now. No, not ask the question. We have asked the question before and failed to answer it. But we have to accept that we really have no understanding of how, you know, vacuum energy couples to gravity. Because if it really couples as Einstein told us energy density couples, then we should not be here. At a time of 10 to the minus 10 seconds, the vacuum energy of the standard model should have sent us off into exponential expansion or into collapse. We can't even predict the sign, right? Instead, we are here 10 billion years later. So that is the real problem. So I have to be honest with you, I don't know. I have, much better minds than mine have tried to solve this problem and not made progress. But there is something for young people left to do. Isn't that a good thing? You know. Yeah? So just one more question. Yeah.
In the paper that of Starobinsky, Shapilov and Sahni, they find a model-independent way of baryon acoustic oscillation measurements, and they apply the Ohm diagnostic to characterize the dark energy behavior.
Yes, yes.
And they find that dark energy goes to some negative energy density passing below
Right.
energy density
Yes.
passing below 0 at nearly z equals to 2.3,
Yes.
I don't know. And same things can be seen in the Bose collaboration paper about the dynamical dark energy.
Yes.
Non-monotonic behavior when they look for the equation of state of dark energy. What do you think about the measurements and these types of
Well, Armand Shafilou was actually my postdoc. In fact, I showed you the results from a couple of papers we did together. This Ohm diagnostic that he developed, actually it was with Varun Sahni. He was Sahni's student in Pune. That is a diagnostic that would work on data. It will tell you the sign of the change, right? That's perfectly nothing wrong with that. Unfortunately, what they applied it to was not was data from Union 2, a previous catalog, which had already been massaged to fit lambda CDM. Okay? Because what people do is, schematically, they adjust the error bars on each point of data point by an arbitrary amount till they get a fit with a chi-square of 1 per degree of freedom to the assumed model. So in other words, they have already fitted a model with the data and then they put that publicly. So you can't use that data then to test any other model, right? So there's nothing wrong with their method of Shafilou and collaborators. But they did not apply it to the, well, not through any fault of their own. The public data set they applied it to was not appropriate, okay? So these wiggles and oscillations, all the stuff you can find when you mix together different data sets, each of which has been fitted to data into a model. The BAO I told you is all done by a template. That template is again lambda CDM, okay? So I don't know how to say this. If you find anything odd in that data, it means that the guys who did the fitting to the model did not do it well enough, because you should really recover lambda CDM from the data, nothing else. That is what it was fitted to, right? So that is what I would say about that paper. Yeah.
Sorry, I have a question on this. So what you said is actually a property of the standard cosmological law. That the acceleration of the universe decreases and actually changes sign around a redshift of 2.
It'll go positive, yes.
And so that time dependence, I thought, was reflected in the supernova data. So just directly, if you assume isotropy, as you said, and you plot the acceleration against the redshift,
Yes.
you actually see that trend.
Yeah, so actually I'm trying to find, that was in fact, just give me a second, I'll find it in my lecture notes from the first lecture, which actually had that. Just one second, please. So yes, there is a change in the sign of Q naught at around redshift just below a 1, where it then goes below the horizontal line. That's what you're alluding to. And what that means is that, was it lecture 2? Yes, I think it was lecture 2. Yes. So this is, yes, this is what you are referring to. Let me just make this thing full screen.
Yeah, what should average these points?
Yes, yes. So you are talking about the fact that one averages these points, assuming they're standard candles, and then you find this, they follow this line where it goes positive and then turns down. There is actually this Hubble telescope supernovae. There were a dozen observed from the Hubble Space Telescope, which actually gave you that thing, right? That turned down.
This picture, but if you average the points
Yeah.
in the same Z,
Yeah.
it looks much better.
Yes, I know it looks much better. This is the latest data set, okay, including all the 50 points that were used to make that inference, plus several hundred that have come since. And this is what the data set now looks like, okay. Maybe I can make this thing a little bit bigger so as to emphasize. Yes. So you can now see it here. So, okay, I think that shows it reasonably well.
It's
So,
very hard to see from this picture.
yeah, so
The
the,
line is a better fit than the red dotted line.
that's right. So the blue line is the one that is changing sign, as you say,
But
right?
actually it is.
Actually what?
Actually, the blue line is a better fit than the dotted line, even though
The blue line is a better fit, yes, the blue line is a better fit at 2.8 sigma, yes, that's correct. That's what I said. It is a better fit at 2.8 sigma. However, this analysis assumed that the deceleration is isotropic. Now when we allow for the possibility that it is anisotropic, then the significance drops to 1.4 sigma. So that's the state of play. You draw your own conclusions.
so it's, I mean, it's one or the other. Assuming isotropy, that other picture, which you said was very beautiful, but maybe is not supported by the data, actually gets this non-trivial support. If you
Yes, it gets support precisely at the level that we just mentioned.
add more complexity to the model, then you might not have enough data to fit that out. That's
Well,
basically what you're saying.
That is true that there is a paucity of data at a redshift higher than 1, because there you are restricted to observations made from space, since the redshifting is to infrared wavelengths and you can't observe them from the ground. And the Hubble Space Telescope observations, these are done on something called the Good Survey, and only some people have observing time on that, Adam Rees among others. And so that data set came from the Good Survey. They are actually analyzed using a different light curve template from the ones which are done from the ground. So the reason why I'm emphasizing this JLA data set is this is the first time all the supernovae have been uniformly treated with the same template. Then you can actually combine the data. Previously, there were different groups doing different ways of analyzing the data and then trying to combine them, which is always a dodgy business. So the current state of play is what I just said, that you have in this line here, you are right, that there is a discernible difference between that red line and that blue line, okay? One of which is expansion at a constant rate and the other one is accelerating. But that difference is, in this analysis, it was 2.8 sigma. And that you can see better from this plot, this side of the plot here, which is showing you what the inferred deceleration parameter is. So this is constant velocity, this is accelerated universe, this is decelerated universe, and the distribution has a tail going out into the positive region. Okay? So the peak is definitely on this side. But the significance of this being a fluctuation of something from there is 2.8 sigma. That's the statement. So the evidence for acceleration, as we said, we use the word marginal to indicate it is less than 3 standard deviations.